It's spouting Shakespeare right now. We trained it on the complete works of Shakespeare. It's surprisingly coherent, actually. The first thing Gemini said was, "Greetings, Earthlings."
Stop it.
Yeah.
That's Philip. Thanks for joining.
Thanks so much. Yeah, really appreciate you having me on as well. So yeah, company's called Starcloud. We're building orbital data centers, initially to provide cloud and edge compute to other satellites, and then later to compete with terrestrial data centers on energy costs, essentially. So, I mean, and really, we're running up against these huge constraints on energy and water from terrestrial data centers. I think lots of towns and cities are now rejecting huge data center proposals in their neighborhoods for the reasons of they don't want strain on the power grid and on the water supply. And so, yeah, what we're doing is solving that constraint, essentially. We started about 2 years ago. My background is I spent first 5 years of my career on the engineering side and software. Before that was studied applied math and theoretical physics, undergrad and masters, and then spent a few years with McKinsey working with the space agencies of different governments. My co-founder Ezra, who's our CTO, has a PhD in engineering from Imperial, and then spent a decade designing and building satellites. Most recently with Airbus Defence and Space, where he designed NASA's Lunar Pathfinder deployables. And then my third co-founder, Adi, was previously at SpaceX as a principal software engineer. And he was responsible for tracking beams, which enables Starlink for other spacecraft. And then before that, he was 20 years on the data center side with Microsoft, installing the sort of first large GPU clusters in collaboration with NVIDIA and OpenAI. So yeah, we started on this 2 years ago. We started initially looking at space-based solar, and then realized if there was a cheap way of getting the energy consumption part to space, and that is data centers for most new energy projects on Earth, then you could solve one of the biggest problems with space-based solar. Space-based solar is where you have huge solar panels and you try and beam that power down, but you lose most of the power in transmission. Whereas if you can move that data center to space, then you can consume almost all of that power. We've just launched our first spacecraft. It has the first NVIDIA H100 GPU or AI chip in it. It's about 100 times more powerful AI compute than has been in space before. And we've done a whole bunch of firsts on that. So we've just trained the first LLM. We've done the first, running the first version of Gemini in space on that spacecraft.
Fantastic.
And we'll be soon running high-powered inference on SAR data in collaboration with various DOW entities.
I was going to ask you about the health status of the GPU that's up there in orbit. So it sounds like you've now just started to kind of run those models and test it, because it's the first time. And just to explain to people, but radiation, I mean, no one's ever run a GPU with that level of radiation before, right? And it's just like a colossal amount more than it would ever experience down here on Earth.
Yeah, well, people have run much smaller GPUs, like the Jetson from NVIDIA, but as I say, the one we're running is about 100 times more powerful than anything that's been in orbit. So it's the first ever data center grade GPU that has been operated in space before. And yeah, there's just an enormous amount. It's not at all ruggedized, so we've had to completely ruggedize it ourselves in terms of new heat sink, switched out the power supply, casing, DC to the AC converter we switched out. Yeah, AC to DC.
And fantastic. Well, so we'll get on to the technology. I just want to come back to the origin story of Starcloud. I mean, as soon as I saw the headlines that you were sending up the GPU up into orbit, I was kind of like immediately like, what is this? Because I hadn't heard of you guys, and I was like, how can this company have escaped my knowledge? And it's because you're so new. And so what I love, Philip, was, and there's so many founders, and I'm a founder myself. We all just love taking on these massive challenges. But what you guys have achieved is incredible. And so I was like watching you on YouTube over there in your kind of office, kind of workshop, isn't it? And I found one quote from you that I absolutely love, and it's this. You said, anything that's worth doing is going to be hard. If something is too easy, it won't have the same potential outcome. So we decided to do the biggest, most ambitious thing we could, and that's build almost all data centers in space. And great quote, but just talk a little bit about the origin story, but also the mindset about how you guys have got this done in such a short amount of time.
Yeah, so the origin story, it started actually about 3 years ago. I went down to Starbase, Texas, where they're building the Starship program. It's this new launch vehicle that is designed to lower the launch costs by between 10 and 100x. And to be honest, it wasn't a work trip or anything. I'm just a huge space nerd, so it sounded like a fun weekend sort of thing.
Yeah.
And but when I was down there, what really struck me was the not just the fact that this new launch vehicle is going to lower the cost. What's really interesting is the capacity is going to go up by an enormous amount, maybe 1,000 times or more. And the reason is they're building these two Starship gigafactories. They're the most enormous buildings. I think they're the largest buildings in the world. And it's designed to produce 3 Starships a day. And I mean, it's just mind-blowing capacity because you can, yeah, it's crazy. It's absolutely crazy. Because they're reusable, if with the current launch vehicle Falcon 9, if you build a new one every day for a year, at the end of the year you still only have one Falcon 9 because it's dispendable. Whereas if you build a new Starship every day for a year, at the end of the year you have 365, and they have 5 times the payload capacity of the Falcon 9. They can fly 10 times as frequently. So it's just completely mind-boggling what's about to happen with the capacity. So
Yeah.
that got me thinking about this concept from, in the 1940s, Isaac Asimov was writing about like the space-based solar, which is where you have these huge solar panels and you beam the power down. The main conclusion we came to was, well, most new energy projects on Earth are being used for data centers. And so either directly or indirectly, it looks like that power is going to be contributing to data centers somehow. So then, yeah, that's how we came to the idea of space-based data centers. But I would credit the speed we're moving mainly to my co-founders, to be frank, because they have basically built by hand that first spacecraft, and we're still only a team of 12 engineers. People are often shocked that we did this all with, I mean, the first spacecraft we did with 3 engineers, maybe 3 or 4, and that's just because they have the experience already. And Ezra's been building
Yeah.
satellites for 10 years. But it's also sort of mindset thing. We are very deliberately staying aggressively lean and engineering focused as long as possible. At the moment, I'm the only sort of product and commercial type person in the company. The rest are all engineering from SpaceX, Kuiper, AWS, Azure, like proper hardcore engineers.
Yeah, so you just kept it lean. You got focused on the problem statement, and then it seemed like you just solved stuff in house. There just didn't seem to be this like, oh, we've run into a problem. You just test it, fix it, come up with the solution right there and then in house. Maybe not right there and then, but certainly in house.
Yeah, exactly. Yeah.
So you've got the GPU up into orbit right now. You mentioned that you've been already running some models on there. I think you mentioned Gemini. What's the goal for you, Philip, with this first launch?
Yeah, I mean, just the very first goal is proving that we can actually run this H100 in space. So people were worried about 2 things. Lots of people actually thought for a long time you just couldn't do it on a chip that powerful in space. So number one was the heat dissipation, and number two was the radiation. And so in order to solve those, we've come up with a pretty innovative cooling solution for the chips I mentioned that involved replacing the heatsink on the H100. And then we actually submerged the entire motherboard, chip, power subsystems, and everything else in this phase change material that melts. So it's pretty, I don't think anybody's ever tried to do anything like that before. Then for the second one, yeah, and the other thing on radiation is that just requires a lot of testing. So we put a whole bunch of H100s in a cyclotron for proton, like beam particle accelerator. And then for heavy ion, we went down to Brookhaven National Lab because they have a particle accelerator there for heavy ions. So I think the only people in the world that know where an H100 will fail if you blast it with these high velocity protons and heavy ions now. And that informs then our choice of shielding, so we can have a lower mass on the shielding side of things. So yeah.
So you've ruggedized it essentially. I want to come on to heat dissipation
Yeah.
because you've also said actually we are a radiator in space company was I think the term you used, and that sounds like an incredible challenge that you're focused on. But going back to the current deployment, so what have you managed to achieve? What are the current results of that H100?
Yeah. Well, we've run, as I said, the first training run of an LLM. We actually trained Andre Karpathy's Nano GPT model, if you're familiar with that.
Okay.
We did, so it's actually, it's spouting Shakespeare right now. So we trained it on the complete works of Shakespeare. It's this model that predicts not just the next token, but it's predicting the next letter. And it's surprisingly coherent, actually, but I mean,
okay.
And then yeah, we've run this version of Gemini. The first thing the first thing Gemini said was, "Greetings, Earthlings."
Stop it. Oh,
Yeah,
that's brilliant.
we've got
That's
the best release
brilliant.
coming out.
So at least we know it's got a sense of humor, so that's good.
Yeah, exactly. Yeah,
So
I don't know
like
what the macro prompt behind that was, but like somebody did well there.
no, well, and I guess well, let's talk use cases because you've mentioned a couple of really interesting use cases and what you're looking to do once you move this from test into commercial. I think you might have your first commercial launch next year, so let me get your perspective on that. But for what's the purpose here initially on the commercial
Yeah,
side of this, Philip? Before you get to the data centers in space piece, how do you
yeah, exactly.
pay the mortgage along the way?
Yeah, so those demos are kind of fun to prove that it works. But the main thing we're doing with this first one is running high-powered inference on SAR data, synthetic aperture radar. That's essentially the satellites that build a 3D map of the world underneath it, and they consume or produce enormous amounts of data, tens of gigabytes of data a second. And right now they're very constrained on how much of that data they can downlink, and so they would like to be able to run high-powered inference on that data in orbit. And
Mm.
so we are going to be very soon with the first spacecraft running inference to be able to detect certain things. So, for example, you might want to know, is there a vessel in this patch of water? And if there is, what the coordinates and which direction is it moving? So that's one thing we'll be doing. The second is, or another use case might be like, is there a wildfire? And that would more be hyperspectral data. And we can then, in much lower latency, in almost real time, we can give those kind of insights back.
Yeah, and the current situation is that there's all these satellites up there providing this data back to Earth, but that they are providing, say, shipping lanes, for example, they all just provide all of the data back to Earth and all of the insights. So the AI inferencing is run back on planet Earth, and
Yeah.
that means huge amounts of data coming down from space to Earth. But what you're proposing is that the data transfer via Starlink to your satellites, and you handle that inference in orbit, and then hand back only the insights back to Earth. Did I get that right?
You did, except that we will most likely receive the data via an optical terminal directly from one of their satellites, or maybe from one of the military transport layers. It's possible it can go through Starlink too, but yeah, we will likely use Starlink for our own backhaul. But in terms of
Okay.
receiving data from a customer satellite, it's most likely could be directly via optical.
Yeah, so you've got a speed advantage for the customer, you've got a cost advantage for the customer. Let's talk. Let's talk about launch economics because I think you've mentioned Starship. I think you're probably waiting for Starship and that huge payload, but it's almost like the business succeeds on the reduction in launch costs over time. Is that
Yes,
correct?
correct.
So what are the launch costs per kilo right now? And where are you looking for them to get to really be in the right place
Yeah.
for a commercial operation?
Yeah, so right now it's about $6,000 a kilo. That is the first business model of providing edge and cloud services to other spacecraft works fine at that price. So that's the initial use case. The break-even point for competing with terrestrial data centers on energy is around $500 a kilo. So about 10x reduction of where we are. The targeted marginal launch cost that SpaceX has for Starship is $10 to $20 a kilo. And they've previously stated they're targeting customer prices of $50 to $100 a kilo. So well within the $500 a kilo range, basically.
So launch costs are coming in. You're satisfied that you can see that's going to happen. You've also got, I presume, some other options. I mean, it looks like it's getting pretty busy on the space front. You've got Blue Origin. You've got, I think, AWS have got their own kind of program going on. It's getting pretty busy in your world there, Philip.
Yeah. No, there's lots of new launch vehicles coming online. So you've got the New Glenn rocket from Blue Origin. Stoke Space has got their rocket. Yeah, launcher and reusable upstage. Relativity Space is working on a rocket, and then Rocket Lab obviously is also doing something. And then
Uh,
beyond that, the Chinese are also working on something. Not that we can launch on the Chinese, but they will help with pricing pressure on SpaceX and others, I think.
Yes, that capacity, yeah, it will all help drive it down, won't it? So then turning back to the technical challenge, so that if you look into kind of like why wouldn't this work, and you've mentioned yourself that heat dissipation via infrared, and I wouldn't mind you just explaining this, please, because I'm now
Yeah.
throwing around terms that I can understand conceptually, but I don't fully understand to the necessary level of detail to talk about them. But it sounds like heat dissipation. It sounds like you've got the solar energy covered. It's
Yeah.
the so that brings power. It's the heat dissipation and the dissipation of a data center. Is a data center is super hot. We have cooling issues here on planet Earth, right? That's the whole back to the whole energy driver and liquid cooling and the impact on the environment.
Yeah. So the way that a terrestrial data center keeps cold is you either blast air past the chips, or um you're essentially evaporating off fresh water, so you can have direct to chip liquid cooling, and then that fresh water goes out to a cooling tower, which is most often is just evaporating fresh water. So you don't have air or fresh water in space, and so you need a new way of doing that. So you don't have convection or conduction essentially, and the way that you do that is you need a large surface area that essentially glows in infrared. Everything in the world is glowing in infrared. Like if you had a heat camera on your face right now, you'd see that your face is glowing in
Yeah,
infrared.
I'll bet.
And so and that what that just means is you're just emitting energy in infrared, basically into deep space. So yeah, that's what we do. We need to keep a large server at a certain temperature, and then that will emit that infrared.
And why is that difficult?
It's difficult because large surface areas need to be folded up for launch, and then they need to deploy. And so you can imagine you've got all this piping for a fluid which is going to go past the chips and then out to this large surface area. And so all of that piping needs to fold up and then expand out to this much larger surface area once we get in orbit.
And so when I look at the kind of graphics and the animation on the Starcloud website, and you're seeing this giant expanse of kind of, well, I think 4 kilometers by 1 kilometer. Is that the infrared, or is that the solar? Is that the heat dissipation, or is that the solar?
So the 4 kilometers by 4 kilometers is the solar, and then 4 kilometers by 1 kilometer is the radiator on the back of that image there. And so yeah, you can think of it roughly 1 square meter of solar panel can produce about 200 watts per square meter in space, and 1 square meter of radiator can dissipate about 800 watts per square meter, maybe slightly less. And so if your surface area on the radiator is a quarter the size of on your solar panel, then that trade-off roughly works.
And you've got so much room in space, so that's not the issue. The issue is getting it up there and almost constructing such a large thing up in space. Do you guys have a plan for that now? Or are you like let's just solve one problem at a time?
Yeah, we have a plan for constructing this radiator in space. Yeah, we have that's basically the core challenge of our engineering team, is building this very large, low cost and low mass deployable radiator. Yeah, it's a core IP, so I won't go too much into that.
Sure. And what's the time frame around the data centers in space? Do you kind of like get to build up as do you have a roadmap of kind of like commercial deployments that build up to this eventual huge data center capacity up in space?
Yeah, exactly. So we're launching our second satellite in October next year. That's going to have about 100 times the power generation of the first one, and by far the largest commercial radiator in space. It will also fly the Blackwell chip from NVIDIA, so that's the newest line. Then a year after that, we'll launch. That's about a 10 kilowatt satellite. Then a year after that, end of 2027, early 2028, we'll launch a 100 kilowatt satellite. roughly, you can think of that as the Starlink version 3 PES dispenser form factor. And then we scale up from there all the way up to a 40 megawatt full Starship payload bay size in the early 2030s. That's about 100 tons. And my expectation is we won't be docking anything together in space for a much longer time, maybe 10 years at least. But we will be just launching continuously these full 100-ton Starship payload bay size spacecraft.
Yeah, that's absolutely fascinating, Philip. Just what an amazing achievement to get this far this quickly. It's just absolutely stunning, and yeah, wish you and your team the very best of luck going into next year. And it's so good to have you on this week when you can actually start releasing the first findings, because I was wondering, yeah, kind of how's the GPU getting on up there, but it sounds like, touch wood, everything, the going is really, really good at the moment, it sounds like.
It is, yeah.
Perfect. Well, look, thank you for coming on AI Outcomes. We will stay in touch with you for sure. Really interested to see how you go. Yeah, I think that covers all of my questions. We could go on for forever, but I want to get you to your hard deadline. We agreed 30 minutes. So, Philip, thank you very much for joining us this morning. Pleasure to meet you.
Yeah, likewise. Thanks so much for having me.
All right. Thank you. Bye-bye. Bye-bye.